All right, 1.8, we're going to focus on density for 1.8, and as we've learned in the past, density is simply the mass of substance per unit volume of that substance. So let's take a look at a pictorial example of what I mean by this. Let's say I've got two balls. I've got a ball on the left and a ball on the right, and they've obviously got different sizes. And if someone were just to ask you, okay, which one is bigger, you would say, well, the one on the right is bigger. But bigger can mean a whole bunch of different things. So if maybe that same person said, well, which one's more massive? Well, you'd probably use your common knowledge to look at it and say, well, I think the one on the right is more massive. That might not always be the case because it actually depends on the amount of stuff that's inside of the objects. So let's say that the one on the right has some stuff, but that stuff is spaced really far apart. And then the object on the left, the ball on the left, has some stuff, but that stuff is not spaced far apart. Actually, it's very, very compact. And so if we just counted the number of particles, let's say they're the same type of particles. The particles on the left would be, there'd be more of them than the particles on the right. So we'd be wrong in saying that the object on the right is more massive. Well, the object on the left is more massive, which is a little bit counterintuitive until you understand the ideas of density. You then would say, well, the thing on the left is more dense. It's the idea of, like, you know, the lead brick being heavier than the entire truckload of down feathers, goose feathers, or whatever it may be. All right. So that's density in a nutshell. And I know we've practiced it a lot before in chemistry and physical science, so we should have a pretty good grasp on it. All right. Bear with me here. Common units for density. Since density is defined as mass per volume, we're going to have a mass unit over a volume unit. That should make sense. So our common mass unit is the gram. That's what we'll use most often here in chemistry. And then we have two different common volume units, centimeters cubed and milliliters. Centimeters cubed for us, we'll use that quite often when we're talking about gases. Gases are often measured in centimeters cubed. Milliliters more often used with liquids. So since we'll be focusing mostly in the laboratory on liquids and gases, those are the two units that we use. And there's the common equation for density. Density equals mass divided by volume. All right, so just an example. What is the mass of a 49.6 milliliter sample of liquid which has a density of 0.85 grams per milliliter? And you'd probably go ahead and use your unit analysis or maybe just understand what that particular equation is. Go ahead and fill in your unknown, and then hopefully you come up with an answer like this. You got about 42 grams. That's the mass of that particular sample. So we're going to be doing a little bit of density work in the laboratory, and that'll actually carry out throughout the semester. All right, 1.9 now. This is the last section in this review unit, this section 1, and it's just going to talk about matter and the different ways that we classify matter. So matter, for definition, is just anything that occupies space and has mass. So everything that you look at as you look around your room right now is matter. Okay, light is not matter, but everything else is matter. Matter exists in three states, as we know. There can be a solid state, a liquid state, and a gaseous state. There are other states. I'll get to that in a slide in a little bit that are a little bit less common, at least to us. To be honest with you, the most common state is not one of these three. But I'll get to that, like I said, in one other slide. So let's take a look at what differentiates these types of states of matter. You've got solid on the left. Look at the particles of the solid. They're very close. They're actually combined. It looks like they're attached to one another. And that's what defines that solid. It's a rigid structure, doesn't move, doesn't really change its shape if outside conditions aren't changed. And in this example is water. So obviously if we heat the water up, what's going to happen? Well, the molecules are going to change around a little bit. Now, water is very, very goofy. It's actually less dense in the solid state than it is in the liquid state. That is why ice floats in the winter. That's why you can walk on water and you can go ice fishing. So if you'll notice those liquid water molecules, they don't seem like they're very far apart. They're a little bit closer together, actually, than the solid ice molecules. That's because the solid ice forms a very tightly packed, or loosely packed crystalline structure, rather. The liquid molecules, however, are moving around a little bit more. They're a little bit easier to put your hand through, obviously. It's hard to punch through ice, but easy to punch through water. So they're a little less rigid, I should say. And then the gaseous particles, obviously, the particles are very far apart. they're moving at very high rates of speed. So we can connect this to what we call the kinetic theory of matter, in that particles are always moving around. They always have some type of kinetic energy associated with them. But as the state of that matter progresses from a solid to a liquid and then eventually to a gas, that kinetic energy actually starts to increase. Those molecules start to move quicker. All right, so I hope we understand those states of matter. We've seen those for years. Other states of matter, the plasma. Remember I said the most abundant state of matter isn't one of these three. Plasma is actually the most abundant state of matter. Everything that you see in a star, that quote-unquote fire that you see, is plasma. It's an electrically charged gas. So take a gas and get it really, really hot. Actually, you don't have to go to a star to see plasma. Just have a campfire in your backyard or light your house on fire. I prefer the former, not the latter. That is an example of plasma. Okay, anytime you see fire, it's plasma. And so that is actually the most abundant state of matter in the universe. One other type of matter that is kind of goofy that you might run into is a Bose-Einstein condensate. This is a condensate that forms near absolute zero. That's negative 273 degrees Celsius. That has superconductive powers. So we've actually started to use these now in some applications. Supercooled rubidium gas would be an example of Bose-Einstein condensate. Nothing you need to really worry about come test time, but just some interesting tidbits of knowledge for matter. So obviously, not everything is a pure substance. Not everything is like pure water. Not everything is like pure gold. We do have mixtures, and actually most of the things that you see around you are mixtures. Mixtures have variable compositions, whether at the macro level, so we can see them, like gravel, or at the micro level, so things that we can't see, like sugar water would be an example there. A homogeneous mixture is the first type of mixture. It has having visibly indistinguishable parts, so a solution would be a great example. So as I said before, sugar water is a homogeneous mixture. Your blood is a great example of a homogeneous mixture. And the other type of mixture is a heterogeneous mixture. These are having visibly distinguishable parts, so we can actually see the differences between the two. Gravel, again, being a good example there. So let's just go for a concept check here to see how you're doing. Look at the following 5 things. Which of the following is a homogeneous mixture? Pure water, gasoline, a jar of jelly beans, soil, or copper metal. And hopefully you've guessed right, it is gasoline. Gasoline is actually a homogeneous mixture made up primarily of octane. We now have other things that are placed into our gasoline. Ethanol, one that is quite popular around here. And we also have fuel stabilizers that are placed in there to help your engine work better. And you'll also notice that you get worse gas mileage in the winter than you do in the summer. And one of the reasons is because the gasoline blend is different. So some of those parts, some of the molecules that are actually in your gasoline are different in the winter than they are in the summer to prevent that gasoline from clogging up. All right, so we can actually change matter from one form into another. One of the simplest ways to do this would be to be able to heat it up or to cool it down, to freeze it, or to boil it. So these are called the physical changes, when we change the form of a substance but not its chemical composition. So we boil water or we freeze water. Obviously, it's still water, but we're changing the type of composition. We can use this quite often, and in fact, we do so to actually purify compounds, to filter compounds, or to just separate them out so we can take a look at individual components. So those 3 things there on the bottom of the page, distillation, filtration, and chromatography, all 3 of those methods can be used to separate out mixtures. And we'll talk about those a little bit more in class time when we start drawing molecular level diagrams in our groups. We'll actually do a couple of these things, specifically chromatography and filtration, in a couple of the labs that we do throughout the semester. All right, so when we say we can separate things out by physical means, it means we can separate them into pure substances. Distillation, so if you had salt water, you could distill the water away from the salt so that you'd have a pack of salt and you'd have pure water on the other end. A magnet could be used to separate out iron filings from a sand composition or a sand mixture. Now, a chemical change is a little bit different than a physical change. A given substance becomes a new substance, or substances, plural, with different properties and different compositions. So an example here would be lighting a Bunsen burner. The methane, the gas that's coming out of the burner, reacts with the oxygen in the air and then gets a little energy from the spark that you create to form carbon dioxide and water. So that's an example of a chemical change. Here we've got an organization of matter chart, a table. It just says that you've got matter as like the overriding biggest thing. So that's what's on the top of your flow chart. That's way up here. Does it have a variable composition, it asks? Well, if it doesn't have a variable composition, then we can actually follow our line down here. And if it's non-variable, then it's a pure substance. If it is variable, then it is a mixture. Let's go over by the mixture area. Is it distinguishable visibly? Yes. Then it's heterogeneous. No. Then it's homogeneous. Over on the other side, where we come to pure substances over here, we can ask, does it contain various types of atoms? If it does, then we have a compound. If it does not, then we have a particular element, and that element is made up of atoms. Okay. The compound, in general, is a combination of those atoms. So if we want to think, well, what's a compound? Water's a compound. Salt's a compound. Carbon dioxide's a compound. Okay, what's an element? Carbon, oxygen, lithium. Okay, those are all elements. Alright? So that's how we classify matter using a flowchart. Flowcharts are nice for us to be able to kind of visualize things and break things down. You'll create some flowcharts for labs throughout these next couple of semesters. So your final concept check then, before I'm done with this little flipped PowerPoint. How many of the following are examples of a chemical change? Take a look at those, see what you think, try to pick them out, and hopefully you only circled one, and that is burning of wood. Alright, so that's 1.8 and 1.9.